Okay, what I'm going to start out with right now, got the quiz up here. And I'm going to explain to you what Po2 and PCO2 are. All right? And then I'm going to have to leave the second part of that question. I'll have to leave that alone for a little bit until I can explain to you the oxyhemoglobin dissociation curve, and then that will explain it better. So what I'm doing right now is I'm going over number 6, the first part. What is Po2 and what is PCO2? We talked about the fact that we talked about Dalton's law and the law of partial pressures. So what I like to do is, again, simplify things. So what I'm telling you Po2 is, or the partial pressure of oxygen, is simply, with respect to the body, is the amount of oxygen dissolved in blood plasma. So you can dissolve gases in a liquid. We've established that on Tuesday. So Po2 is simply a measurement of how much oxygen is dissolved in the plasma. And it's measured as a pressure. So just like your tires have air in it, that's measured as a pressure. So PCO2 is the same thing. It's the amount of carbon dioxide dissolved in plasma. So one of the ways that you transport oxygen and carbon dioxide is dissolved in the plasma. It's not the best way, but it is a way. And it's measured as a pressure. And rarely do I ever ask you to learn specific numbers, but in this case, I'd like you to know the normal arterial values for Po2 and PCO2. So the arterial value of Po2, the normal range is between 80 and 100 millimeters of mercury. And then PCO2, same thing. And again, we're talking arterial blood. The PCO2 levels are between 35 and 45 millimeters of mercury. So, and again, these are measured in people who are really pretty sick. They got a lot of stuff going on. And the reason that you don't measure these routinely is that you have to actually puncture an artery in order to get these values. So you don't want to be routinely puncturing people's arteries for that. So that's that. That's Po2 and PCO2. Now, yeah?
Just measured in the arteries, not the venous?
You can measure it in the venous blood, but that really doesn't serve any purpose, because what you really want to look at is you want to see is, are the lungs able to get rid of CO2, and are the lungs able to take on O2? And then the metabolic demands of the body would change the amount of Po2 and PCO2 in venous blood, so that really doesn't tell you a lot. So again, in rare cases, and only if people are really sick, so they typically only do these in the emergency room or in the ICU.
So these levels change in the venous but not the arterial?
Right, because your pH has to be maintained, your PO2 has to be maintained, and your PCO2 has to be maintained. So if you are using more oxygen because you're more metabolically demanding, right, that means you're also producing more carbon dioxide. So if the respiratory system is increasing the rate and depth of breathing, then that extra CO2 will be expelled, and the amount of the PCO2 and PO2 of arterial blood, regardless of whether you are sedentary or you are active, should be within these ranges. Okay, so let me explain to you why clinically this is important. If I can get here. Sorry about that. Wait, I think I have this up. Sure. What's that? Yeah, that's something they would measure. The other thing that they would look at is carbon monoxide levels. Carbon monoxide and oxygen compete for the binding of iron on hemoglobin. The problem with that is that carbon monoxide doesn't let go. So basically what you do is you asphyxiate yourself because the carbon monoxide will bind to the iron and it won't let go. So people who die of carbon monoxide poisoning, they actually look wonderfully healthy. They have nice rosy cheeks and they look perfectly fine, only they're dead.
Could that like prolong the time between the time that they die and the time they start rigor mortis?
No, not really. The only reason that carbon monoxide binds to the iron and will turn the blood red just like oxygen will. That's why they have that nice little rosy red color. Yeah, but they're dead. Okay. Here's the other thing. Students when they get into clinical, they always struggle with this concept. The respiratory system seems to really kind of befuddle students, and I really can't explain it, but it's tough for them. So I'll do my very best to explain it, and hopefully you'll get it.
Seems to trip up the students? Is it like the gases?
Yeah, it's gases and then the acid-base balance. All right, so
your heart is it's a muscle.
all right, so watch. Whoops, it's too far. I would write this down. No. Let me explain. I just explained to you what Po2 is and what PCO2, right? I'm going to have to skip the second part of number 6 until I can give you more information. What I'm going to do now is explain to you why, from a clinical perspective, Po2 is important in delivering oxygen to the cells. Yes? Okay, so that's what I'm going to do. So if you look, you know, is this the highlighter? Right? If you know this, that approximately 60%, that's not a good color, approximately 60% of blood is 0.9% sodium chloride or normal saline. We know this, right? So when someone comes into the emergency room and they're bleeding red blood cells and plasma as well. Now, I would really consider writing this down. You have a red blood cell, and within that red blood cell, you have the protein hemoglobin. And embedded in the hemoglobin molecule, you have iron. And oxygen actually binds to the iron on the heme portion of the hemoglobin. So if you're losing red blood cells, regardless of the reason, then you are decreasing the amount of oxygen transported to the cells of the body. And again, we know and understand the importance of that. So, but when people are bleeding, everyone has a particular blood type. And we know that there's A, B, and O. We know this. But when people are bleeding, you can't look at their blood and determine their blood type just by inspection. Right? I mean, who could? Yep. The line represents oxygen binding to iron. All right? So, because you can't determine someone's blood type, you still have to deliver oxygen to the cells of the body. But just a few minutes ago, I explained to you that you can dissolve oxygen in the plasma of the blood. And we learned, maybe, I don't know, I think maybe several weeks ago, that blood plasma is 0.9% sodium chloride. So in the event that someone is bleeding a lot, what you will do is you will start large bore IVs, right? So big IVs into their veins. IV stands for intravenous. So you're putting a needle into a vein. And you will give them saline. And instead of breathing 21% oxygen, which is room air, you give them 100% oxygen. So if you look at what the normal values are for Po2 of arterial blood, the normal values for Po2 are 80 to 100. But that's on room air, which is 21% oxygen. So if you bump up that person's oxygen to 100%, right, then you can increase that Po2 to like 600. So basically increasing the amount of oxygen delivered in the plasma by a factor of 6. And that is typically enough oxygen to keep the person viable until you can find out what the person's blood type is and then give them red blood cells. So that answers that question. And that question was, explain why, from a clinical perspective, Po2 is important in delivering oxygen to the cells. So I have done that.
It's because you raise the amount of oxygen so that it can be dissolved in the plasma?
Oxygen is dissolved in the plasma normally. All you're doing is increasing the plasma, so you're increasing their blood volume, and delivering more oxygen dissolved in the plasma.
And you're increasing the volume by giving the normal saline.
Correct.
And then upping the oxygen by giving the oxygen.
Correct. Yes?
Would this be one of the situations that you place a catheter also? Because you're giving them the big bags, and wouldn't that increase the volume so that they would...
That you're going to make sure, you want to make sure that even if they're bleeding, once you stop the external bleeding, you want to make sure that there's no internal bleeding going on. So that will solve that too. So if they're losing blood volume, you give them blood volume. And the blood volume, the plasma is 0.9% sodium chloride, so that's what you give.
Would it be in every situation that you give that?
No, in burn cases and things like that, you will you give a IV solution called lactated ringers. It's basically physiologic plasma, so it contains electrolytes, contains bicarbonate, things like that. So when you get into clinical, you're going to learn about the different types of IV solutions that you give and why you give them. So that's number 6. And just so you know, I'm going to come back to this part of number 6. All right? Okay. Did I cover the PO2 and PCO2 at the level of the alveoli, and then in the cell, did I go over that or no? Do you know? Okay, so let's start there. So what I'm going to do, just so you know, I'm going to answer number 7. 7's a pretty basic question. One second. Okay, so 7's pretty basic. If you look, you cannot blow out all of the oxygen that's in your lungs. The reason you can't is due to the effect of that negative pressure that's in the pleural space, and we talked about that on Tuesday a little bit. So when you try to blow all of the air out of your lungs, there's still some air left in your lungs. And the air that's still left in your lungs after you try to blow all that air out is called your residual volume. So the residual volume of the lungs is the amount of air that's left in after you try to blow all that air out. And as you age, that residual volume goes up. There's nothing you can do about it. The lungs become less elastic, and if you smoke, then that can damage the alveoli, which further increases that residual volume in the lungs. But my point is this, that the amount of oxygen, or Po2, in the residual volume is relatively low. It's about 40 millimeters of mercury. But if you recall from on Tuesday when I explained to you that the Po2 of the air that you breathe at 1 atmosphere, we did the math. The Po2 of the air that you're actually breathing is 160 millimeters of mercury. Now, if you were able to blow all of the air out of your lungs with each breath and then bring new air in, what that would mean is this. Hang on, this is really cumbersome. That if you're able to exchange air completely, then the Po2 in the alveoli would be 160 millimeters of mercury. So if you were able to do that, but of course we can't do that. So what we have to do is we still have to deal with this residual volume. And because this residual volume has a relatively low Po2 because the oxygen is leaving the alveoli and going into the blood, so what you do is you mix the Po2 of the air that you're breathing in from the atmosphere, which is 160, and then you mix that with the Po2 of the residual volume. And if you do the math, just real simple, you add those two together and divide by 2, the Po2 of the alveoli comes out to about 100 millimeters of mercury. So that's where you get the 80 to 100. So the question is, explain why Po2 of atmospheric air is higher than the Po2 in the alveoli. Well, that's because of the residual volume, the relatively low Po2, and then when you breathe in that Po2 of 160, it mixes with that residual volume that you can never get rid of, and then if you average those two together, the Po2 comes out to about 100.
And then is the 40 millimeters of mercury, the residual, is that per lung?
Yeah, and it's basically I don't want to get into too much craziness, but when you take a breath in, there's still air in there, and that air is going to diffuse, right? It's going to spread out evenly until you equalize the PO2 within the lungs. Okay, so that's that. All right, so this is what I want to do. I want to show you this. That's why understanding the circulation of blood through the heart. And and at least at some level understanding the byproducts of metabolism and how they affect your physiology. That's why I gave you that one question because that one question is now going to help explain how oxygen is delivered to the cells. So, and it's really the result of metabolism in the cells. And I hope that you appreciate, at least to a little degree, why I spend so much time on metabolism and why understanding that is important. So let's get into this. I'm just going to tell you this. Remember that the right side of the heart pumps venous blood. And venous blood has a Po2 of 40. The reason the Po2 of venous blood is lower is because the oxygen moved by pressure from the plasma into the cell where it could be used for metabolism. So again, these are pressures, right? High to low. We've just established the fact that this is an alveoli. And then again, this is a pulmonary capillary. We'll just put P cap, but you know that as a pulmonary capillary. And when we breathe in air at 1 atmosphere, the Po2 of the alveoli is 100 millimeters of mercury. What's the Po2 of venous blood? It's 40. So by pressure, oxygen will move into the plasma of the blood until the Po2 of the alveoli and the Po2 of the blood plasma is equal. It's 100. Now, if you only took one breath, then the Po2 in the alveoli and the Po2 in the blood would be different. So it would move until both had equal pressure. The reason it's 100 here is because you are continually replenishing that oxygen by taking breaths in. That's why you maintain that Po2 of 100. So again, this Po2 is the amount of oxygen dissolved in the plasma of the blood. And Po2 affects how much oxygen is actually carried by a red blood cell. But we'll cover that a little bit later. Now, as you know, then all of this newly oxygenated blood, and right now we're just talking about the plasma, that is going to go to the left side of the heart, right? And left atria, left ventricle, and then it's going to go down to the cells of the body. So if we look, the Po2 of the blood that's being sent out by the left ventricle is 100 millimeters of mercury. And the only place that nutrients and gases are exchanged is at the level of the capillary. So if a physician wanted to find out what the Po2 of the person's arterial blood is, they don't have to put a needle into the left ventricle. They could put it into a large artery because there's no gas exchange in the arteries. There's only gas exchange at the level of the capillary. So let's look at this. So what we're going to do now is we're going to come down to the level of the cell, right? So if we draw our stupid picture again, that'll help explain it. So if you recall, you have an arterial end of the capillary, then you have a venous end. Now, this should be obvious by inspection that the Po2 of arterial blood is 100 millimeters of mercury. Where do you want the oxygen to go? Well, you want it to go from the plasma and into the cell. So in order for that to move by pressure, the Po2 inside the cell has to be lower than the Po2 of the arterial blood. And of course it is. So the Po2 inside a cell that is, basally metabolically active is 40. So the oxygen will move by pressure from the plasma of the blood into the cell to allow aerobic metabolism to occur. And that oxygen will move until the cell and the blood are in equilibrium. So that's why the venous blood is 40 millimeters of mercury. So again, one of the ways that oxygen is transported in the blood is dissolved in the plasma, and it's measured as a pressure.
So is the PO2 in the cell 40 after the PO2 from the arterial end gives it, or is that a constant?
At a basal level of metabolic activity, it's a constant because the cell is constantly using the oxygen. So if this was a muscle cell and you got up and you started running, that cell is going to use more oxygen, and therefore the PO2 inside that more metabolically active cell will drop. And that's a good thing because when it drops, now there's a greater pressure difference, so more oxygen will be delivered that way. So it makes really, really good sense, I think. So what happens to all the venous blood? All that venous blood now comes back to the right side of the heart. What was the PO2? It was 40. And what's the PO2 in the alveoli? 100. So that cycle continues. Now, let's just do the opposite. The opposite of oxygen, well, maybe not the opposite, but you know what I'm talking about. So let's look at the cell. And what does the cell produce? The cell produces carbon dioxide. And the carbon dioxide will get dissolved in the cytoplasm of a cell. And the PO2, or the PCO2, I'm sorry, the PCO2 of a cell that is at a basal level of activity is about 45 millimeters of mercury. Now, where do you want the CO2 to move by pressure? You want it to move from the cell into the blood. And it always moves from high pressure to low. So the pressure of carbon dioxide in the arterial end would have to be less than 45. And of course, it is. Now, if you notice the pressure difference between PCO2 and PO2, the difference here in carbon dioxide, the partial pressure is much smaller. And the reason for that is carbon dioxide is about 20 times more diffusible than oxygen is. So you don't need a huge pressure difference, in that pressure gradient to get carbon dioxide to move. Now, and once CO2 moves from the cell into the plasma of the blood by pressure, it's going to equilibrate, and the PCO2 of venous blood now becomes 45. And as we learned from quiz number 1, we learned that CO2 is an acid. So the pH of venous blood is slightly more acidic than the pH of arterial blood due to the increased amount of carbon dioxide present. Now, all that venous blood with the increased amount of CO2 dissolved in the plasma, that's going to come back again to the right side of the heart. Let's see if I can remember this. Well, there, I did it. Oh, that's wonderful. So all that venous blood with the PCO2 of 45 is now going to come back to the right side of the heart. So right atria, right ventricle, and then it's going to get pumped to the lungs. And what's going to happen in the lungs? Well, you're going to exchange gases. So now instead of talking about oxygen, we're going to talk about carbon dioxide. So let's look at this. Again, you have the alveoli, then you have the associated pulmonary capillary. So let's review. The PCO2 of venous blood is 45 millimeters of mercury. You want the PCO2 by pressure to go into the alveoli. So the pressure, the partial pressure of carbon dioxide, clearly has to be less than 45. And it is. It's 40. So the carbon dioxide produced at the cell and then gets dissolved in the plasma. It will move by pressure from the pulmonary capillary into the alveoli, and then you will exhale it. So this newly oxygenated blood and this reduced hypercapnic blood will have a PCO2 of 40. So this is where you get the values for PO2 and PCO2 of arterial blood. So let's summarize here a little bit. Before I do that, let me show you. Explain the ways oxygen and carbon dioxide excuse me, are transported in the blood. Right? So I'm giving you one way that oxygen and carbon dioxide are transported in the blood, and that is dissolved in the plasma and then measured as a PO2 or PCO2. So what's one of the ways oxygen is transported in the blood? As a PO2 dissolved in plasma. The way carbon dioxide is transported, again, PCO2, and then we'll just put a little quotations indicating that it's the same thing. Now, again, I don't care about numbers, but just to give you an idea of what we're talking about, only about 2% of oxygen is transported, dissolved in the plasma. With PCO2, it's about 10%. So that leaves a lot of areas for carbon dioxide and oxygen to be transported in other ways. And that's what I'm going to talk to you about now. Specifically oxygen. Now, this is really important. Well, you'll learn. So, you have a red blood cell. Red blood cell is big. As a matter of fact, it's so big that as it goes through most capillaries, it actually gets squished. And in a red blood cell, you have this huge protein called hemoglobin. And embedded in each hemoglobin molecule, there are 4 atoms of iron. This iron is in its ferrous state. So 3, 4. Now, oxygen is going to move from the alveoli with a PO2 of 100, and the PO2 of venous blood is 40. So as oxygen moves from the alveoli into the plasma, raising the PO2, that is going to cause oxygen to increase its affinity for the binding of iron on the hemoglobin molecule. So, and it makes perfect sense. It makes perfect sense. Where do you want the oxygen to bind to the iron on hemoglobin? Well, you want it to bind in the alveoli and the pulmonary capillary, right? I mean, that makes sense. So, if you work in a clinical setting, right, and you put the little thing on the person's finger, that pulse ox, what it's actually measuring is the amount of oxygen bound to the iron on hemoglobin. That's what it's actually measuring. Now, I'll get there and I'll explain that to you, but I just want to say this out loud now. That the Po2 directly correlates with how much oxygen is bound to the iron on hemoglobin. So if something were to cause your Po2 to drop, let's say that you had a pneumonia, right? So you had mucus and bacteria growing in your lungs. That's going to limit the amount of oxygen that can move into the plasma, and that's going to reduce the amount of oxygen bound to the iron on hemoglobin. So what you're really measuring when you use that pulse ox is you're measuring the amount of oxygen bound to the iron on hemoglobin, and it's measured, and it's called oxygen saturation of a red blood cell, or your O2 stat, right? You've heard of these terms? Okay. So, and in normal physiology with normal functioning respiratory system, no pathology, the normal oxygen saturation of a red blood cell, when all of those red blood cells leave the lungs and start making their way back to the left side of the heart, 96 to 98% of all of those oxygen, or all of those irons, should have an oxygen bound to it. So this is by far the best way to transport oxygen. That's why it's critical in times of trauma or for whatever reason, substantial blood loss. It's really important to know the person's blood type. That's why when a person goes in for surgery, like elective surgery, they will have pre-op labs. And one of the labs that they draw preoperatively is a blood type. That way they will have that blood type on hand in the event that this person starts to lose a large amount of blood. Don't you think that makes sense? Well, there you have it. That's why they do that.
So with an iron deficiency, there'll be a lack of oxygen too?
Yes. So women who have very heavy periods, right, their energy level tends to be lower because they have less oxygen carrying capacity. I don't know if I told you this, but maybe I did. I don't remember. But the thing that holds the oxygen at the end of the electron transport chain is iron. So women who are iron deficient, they have a difficult time holding that oxygen at the end of the electron transport chain. So that impairs aerobic metabolism. That's why monitoring iron levels, especially in women who have really heavy periods, that's important. So do we follow this now? So the second way that oxygen is transported in the blood is bound to the iron on hemoglobin. This is also important. I think people forget this. One red blood cell doesn't have just one hemoglobin molecule. One red blood cell has about 250 million molecules of hemoglobin. So one red blood cell can carry a lot of oxygen. So if you lose about 30% of your blood, your ability to transport oxygen to the cells of your body is going to be impaired. You will be compromised. Now, that's oxygen and how it's transported in the blood. I'll come back to carbon dioxide, but first what I want to do is I want to talk to you about what's referred to as the oxyhemoglobin dissociation curve. Yes?
Did you say
say that there's an affinity between the iron and the oxygen?
Yes.
Did you say why?
Why there's an affinity? The charges. There's the molecular charge on oxygen is actually what do they call it? Bipolar. What do they call that? Where it's a slightly positive end and a slightly negative end. What's that called? Dipole. Dipole. So it's the negative end of the oxygen that will actually bind to the iron on hemoglobin. Now, so, and I'm sorry that these questions, I can't answer them one after the other. Maybe I should have changed them. That way you could just follow in order. But you're probably used to that by now, huh? If you you want me to change the order of the questions? Maybe for the next one. Okay, I'll take that under advisement. Okay. So what I'm going to do now is I'm going to explain to you the oxyhemoglobin dissociation curve. Right? This question is worth a lot of points. Yes, number 4. So number 4, I'm going to go over now. And I'm going to explain to you how this works. Okay? Ready? All right. Now, what I want you to do first is I want you to just think about the fact that oxygen binds to the iron on hemoglobin in the lungs. You simply have to take that on faith for right now. I'll explain more once we get there. Now, you want oxygen to bind in the lungs, and then when that red blood cell gets down to the cell, you want that oxygen to let go and go and sit at the end of the electron transit, right? That's what you want. So, again, it will show you how metabolism will dictate this. So, let's look, and I'm going to take you through it again.
Heart is divided into the right
So,
and left side. Division protects
if you
oxygen
look,
from the
let's just quickly do this, quickly, right? You have a red blood cell, and what's the saturation of oxygen? 96 to 98%, right? And what's the Po2 of the blood being pumped by the left ventricle? It's 100, right? Okay, that's good. So what we, hang on, oh boy. Okay, so this blood being pumped by the left ventricle is going to go down to the cells of the body. All right? Now, I'm sure you all wrote this, so I don't even have to say it. That you know the byproducts of metabolism, right? That's very good. Now, watch. This is important that you need to know this. Yep, you got to be very quiet. Don't make too much noise here. This is really important right here. Okay, watch. I would write this down. Who's going to write this down? Okay. hemoglobin is a protein, right? And we learned that all proteins, regardless of the type, are temperature and pH sensitive. Right? We learned that. That's good. Okay, so watch. Watch. What are the byproducts of metabolism? Don't even tell me, I know them. No, yeah, that's fine. There are hydrogen ions, right? There is carbon dioxide, and there is heat, right? Now, I didn't list them all, but I just want to concentrate on these guys for the moment. So, as that blood leaves the left ventricle, and it is going to go to the most metabolically active parts, because not only are these byproducts of metabolism important in terms of delivering oxygen and stuff, but they're also arterial vasodilators. So when the left ventricle contracts, that oxygenated blood is going to take the path of least resistance and go to the most metabolically active parts. See? You see this? Good. Now watch. As that blood, which is going to the most metabolically active parts of the body, right, through those arteries that are dilated, gets closer and closer to those cells, the temperature of the blood is going to heat up. And as the temperature of the blood heats up, it is going to change the shape of hemoglobin slightly, and it will not allow the oxygen to bind to the iron. So the oxygen will fall off and then go from high to low. So as we can see again, and of course this is perfect, it is metabolism and the byproducts of metabolism that dictate physiology. Isn't that wonderful? I think so. Now, you're not going to believe this, but let's look at this for a minute. The more metabolically active this cell becomes, the more of these byproducts that it's going to produce. And that means a greater change in the shape of hemoglobin. So that means more oxygen is going to fall off and go into the cell. So it is crystal clear that it is metabolism that dictates your physiology. Do you see that? That's excellent. Yep. Now, let's move on from here. I'm sure you probably didn't have time to read that. That's okay. So I'll expect you to read that when you have time. And I'm sure I know that you'll do it. So let's look at the arterial end of the capillary. And let's look at the Po2 of arterial blood. The Po2 of arterial blood is 100, right? What is the Po2 inside a cell? Don't say it. I'll tell you. It's 40. So by pressure, oxygen is going to leave the plasma of the blood and go into the cell. Now this is important. Oxygen will leave the plasma of the blood, the arterial end of the capillary, and go into the cell by pressure. I'm going to write this out. A decrease in Po2 of the plasma causes oxygen to dissociate from hemoglobin. Hemoglobin. That's a hemoglobin. So that's another thing that will cause more oxygen to fall off that iron and go into the cell. Now, let's look at this a minute. As you can see, and if the cell becomes more metabolically active, the PO2 within the cell is going to drop, right? Because it's using more oxygen. So the pressure of oxygen inside that cell is going to drop. That means there's going to be a greater pressure difference between the arterial blood and the cell. So by pressure, more oxygen will go into the cell by pressure, lowering the PO2 of the plasma. And the lower the PO2 of the plasma is, oxygen will fall off the iron easier. So this is how oxygen gets delivered to the cells, and the correct amount of oxygen gets delivered to the cells based on its metabolic rate. Does that make sense? Sure. Now, that's PO2. There is and that deals with the Bohr effect. In your book, the Bohr effect talks about the drop in PO2 and how oxygen will dissociate from hemoglobin. Now, the Haldane effect deals with carbon dioxide. Now watch. What is the PCO2 of the cell? The PCO2 of the cell is 45. What is the PCO2 of arterial blood? That is 40. So the PCO2 by pressure is going to move from the cell into the blood. That will raise the PCO2, and that will cause oxygen to fall off the iron on hemoglobin and go into the cell. So let's look at this. And students are fans of lists. So I will list things for you. Okay? Okay, so I'm going to now list conditions that favor oxygen no longer wanting to bind to the iron on hemoglobin. What's that? Affinity means if you have an affinity for someone, then you want to bind with them. So decrease oxygen affinity means you don't want to bind with them. Okay? So let's look at condition number 1. And remember, these very important. This is at the level of the cell and the systemic capillary. I should have told you that. Let me make this cell and systemic capillary. So condition number 1, an elevated temperature. Condition number 2, a drop in pH, so acidic. Condition number 3, a decrease in the partial pressure of the plasma of the blood. And condition number 4 is an increase in the partial pressure of carbon dioxide within the plasma. All of these conditions will cause oxygen to dissociate from the iron on hemoglobin. And the more of these conditions that you have at the level of the cell and systemic capillary, the more oxygen that will be delivered to the cells. Now, watch. Let's look.
In a year. Oxygen poor blood. Blue
Okay. All the venous blood of the body returns to the right side of the heart, right? Now, what you have to remember is that you are still sending blood to parts of the body that are relatively metabolically inactive. So this is very important. This is very important. Okay? All venous blood mixes in the right atrium. So the much hotter blood from the metabolically active parts is going to mix with the cooler blood from the relatively metabolically inactive. So the overall temperature of the blood when it reaches the right side of the heart is going to go down. So the temperature of that blood, once it gets into the right side of the heart, is going to be lower than it was at the level of the cell. So that blood now is going to be pumped to the lungs. So now let's look at the conditions at the level of the alveoli and the pulmonary capillary. So if you look, here we go. You have the red blood cell, and for the sake of time, we'll just make one iron on the hemoglobin. Okay? So, what are the conditions at the alveoli and the pulmonary capillary? Well, number one, the temperature is decreased, right? Because that warm blood from the metabolically active parts mixes with the cooler blood from the non-metabolically active parts. Let's review. What is the PO2 of venous blood? What's the PO2 of, I'll just tell you, it's 40. No, I'm telling you.
Well, we knew it, at least we were right.
Yeah, well, big wow.
Big wow. It's hard to come by these days.
The PO2 of the alveoli is 100. So watch. What's going to happen to the PO2 of the plasma at the level of the pulmonary capillary and the alveoli? It's going to increase. So condition number 2 is increased PO2. What's the PCO2 of venous blood? It's 45. What's the PCO2 in the alveoli? It's 40. So the PCO2 is going to leave by pressure and go into the alveoli. So the third condition is a drop in PCO2. And then finally, we learned from quiz number 1 that CO2 is an acid. And by getting rid of carbon dioxide in the lungs, that will raise our pH. So these are the conditions at the level of the alveoli and the pulmonary capillary. And all of these conditions cause oxygen to want to bind to the iron on hemoglobin.
And every single one of these occur, right, for that to happen?
Yes. Now, not all of them have to occur, So if you get like an increase in PO2, like you give somebody oxygen, more oxygen will bind to the iron on hemoglobin, right? Just, what's that? Yeah,
It will increase pH because CO2 is in the gas.
yeah. So I did that right.
He's making sure you did it wrong.
Okay. So that, watch. That explains how oxygen knows to bind to hemoglobin in the lungs and then let go when it gets down to the cell. Now, it doesn't completely explain the oxyhemoglobin dissociation curve, which I'm going to explain to you right now. No, I just explained how oxygen knows to bind to red blood cells in the lungs and let go of the red blood cell at the cell. Now I'm going to actually show you the curve. Nursing and nursing instructors, they love this thing. That's good. I think they love it because they know students have no idea what's going on. And that's okay. I don't either. Wait a minute. I think I got a handout on that. Can I look real quick? Do you mind? Oh, here, yep, there it is. I made this like 3 years ago, I think. Oh, there it is. Uh-huh. 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 Okay, are you ready? I'm going to explain this to you. I know anytime you got a graph and you got numbers and arrows, then you got a couple of dotted lines, and you got 3 curves, forget about it, right? Right. Maybe you want to just figure it out on your own. You want some help? Okay, I'll help you. All right. The oxyhemoglobin dissociation curve is sigmoidal. I don't even know what that means.
What's DPG?
That's diphosphoglycerate, which is a byproduct of the red blood cell metabolism, and the amount of diphosphoglycerate increases at the level of the cell and the systemic capillary. That byproduct of metabolism decreases oxygen's affinity for the binding of hemoglobin, causing oxygen to unload from the iron and go into the cell. Here's looking up my old address. Are you ready? I can break this down. I can. But I ain't gonna. I'm gonna give it to you right out of the book. Ready? Here on the left side here, or in math, the y-axis represents the percentage of iron binding to the oxygen. So it represents the oxygen saturation of a red blood cell. Okay? Now, on the x-axis, this represents the partial pressure of oxygen in the alveoli. Now, the sigmoidal nature of the oxyhemoglobin dissociation curve is such that when one oxygen binds to the iron on hemoglobin, the other oxygens bind easier. That's what produces that sigmoidal effect. If it was each oxygen had an equal chance that when one oxygen bound, it made the other ones easier, you would have a linear effect. The sigmoidal effect is the result of the increased affinity of oxygen for iron after one oxygen binds to the hemoglobin. That's what creates that sigmoidal effect. And through evolution or whatever your idea is, it's perfect. Because the normal Po2 is between 80 and 100. And as you can see, even with a drop of Po2 of 20 millimeters of mercury, right, from 100 to 80 is 20. I had to check my math myself. If you look, the saturation of oxygen of that red blood cell does not change much. That's beautiful, because if it was linear, then you go to Denver, there wouldn't be a Denver because people couldn't live in Denver. So the fact is that because of that increased affinity for oxygen after one oxygen binds, that allows us to maintain a good saturation of your red blood cell, even with a significant drop in Po2. Now, the reason there's three curves here is the middle thick blue line represents normal physiology. So it represents a pH of 7.4, a Po2 of 90, and an oxygen saturation of 97. Now, if you look, and nurses, they love using these terms. They really have no idea what they mean. They don't, but they love using those terms. So when the oxyhemoglobin shifts to the right, what that means is that for any given Po2, the amount of oxygen bound to the iron on hemoglobin is less. And when the curve shifts to the right, the whole body is experiencing conditions that are present normally just at the cell in the systemic capillary. So a shift to the right, and what causes a shift to the right, and I'll just say it. You should write this out. I'm just going to say it. A shift to the right in the oxyhemoglobin dissociation curve means that for any given Po2, the amount of oxygen bound to the iron on hemoglobin is less than normal. Do you want me to say that again?
Yeah.
Do you want me to say that again? Do you want me to say that again?
Not that again. What you said.
Oh, the other part?
Yeah.
You need to be more specific. Yeah, see? Right? I'm working on being more specific. When the curve is shift to the right, the conditions are such that for any given Po2, the amount of oxygen bound to the iron on hemoglobin is less. What are the conditions that cause the curve to shift to the right? Well, let's look. There is a drop in pH, so the blood becomes acidic. This is so weird. This is so weird. I'm having a flashback right now to my NCLEX exams. And I remember this question. I'm not even kidding. That was 32 years ago. I took my NCLEX at the Mecca Center in Milwaukee. The Mecca Center. He ain't even there no more.
Is that blue building?
I don't even know. I haven't been there. After I took that, I just never went back. There's a bar there, Major Goolsby. Is it still there?
Yeah, they had it on.
Oh, they did? It used to be kind of like on a corner, right?
It's still on the corner.
Yeah. We went there. It was 2 days, 8 hours a day. So it wasn't like you'd take it on a computer and the answer hunt. You had to sit with like 5 million people in the big Mecca. And then we had an hour for lunch. So we went to Major Goolsby's, and I'm playing that Papa Shot basketball. I was killing it, man. And we were drinking beer. And I am killing that. Like, I cannot miss. And then I look around, and everybody else is gone. And I'm like, that ain't right. So I run back, and they had armed security guards, off-duty police officers, and this guy wasn't going to let me in because it was after that time. And they would check your ID, but he let me in. I said, you know, come on. How about it? But I remember this question. As clear as it was like yesterday. But you won't see it. They took that one off. So watch. Acidosis causes a right shift in the curve, meaning you have less oxygen bound to the iron on hemoglobin. Fever causes the curve to shift to the right. What does that mean? That means less oxygen is bound to the iron on hemoglobin. And increased diphosphoglycerate, well, you don't have to know about that. If you add it, I will simply ignore it and look for the things that I want. So the other things that will cause a shift in the curve to the right are increased PCO2 and decreased Po2. Now, let's look. Let's look, shall we? Who wants to look? Watch. Watch. Wait, where is this thing? I know, right? What the hell? Where is it? Did I erase it? What the? Huh. Wait, that ain't right. Oh, wait. Oh, yeah, we got it here. Oh, look at that. Ooh. Okay, look. Look. Where do you find high PCO2, low pH, elevated temperature, and low PO2? You find it at the cell and the systemic capillary. But when those conditions are throughout the body, something's going on, right? That's going to cause a shift in the oxyhemoglobin dissociation curve to the right. Say yes. Do you follow that? What will cause a shift in the curve to the left? That means that in this little green curve here, that means that for any given PO2, more oxygen will bind to the iron on hemoglobin. The problem with that is that even though more oxygen binds to the iron on hemoglobin, if those conditions persist throughout the body, it won't let go. That's a left shift. Yay! Right, so oxygen, so when the pH is elevated, the body temperature is lower, the PO2 is higher, or the PCO2 is lower, that is going to cause oxygen to bind to the iron on hemoglobin, but it won't let go. We'll end our discussion there today, class. This ends our period of instruction. On Tuesday, when we come back, I'm going to explain to you the clinical significance of knowing the oxyhemoglobin dissociation curve. Sometime over the weekend, probably. Sure. You too.